All right, guys, we're going to be starting chapter 13, which is all about rocks, actually rocks and minerals. And our first section here gives us a little bit of an overview of rocks, kind of exactly what are rocks, and a couple other kind of fun facts that we know about rocks. And then we get more into detail the last two sections. Section 2 is specifically about igneous rocks, and then the third section is about sedimentary and metamorphic rocks. All right, so 13.1. All right. Difference between rocks and minerals. So minerals, if you look at the definition here, are solid, inorganic, crystalline solids with a definite chemical composition. So if something checks every one of these boxes, it's a mineral. So it's got to be solid, it's got to be inorganic, it has to be crystalline, it has to have a definite chemical composition. If it's all of those things, it is what we call a mineral in geology. This is an example of a mineral that we often put on food. The picture on the left-hand side there you can see is kind of like what a molecular structure would look like of this mineral. On the right-hand side is what it looks like in nature. So I can see it's a solid. I don't know it's inorganic, but it is inorganic. I can see it's got a crystalline shape, and it does have a definite chemical composition, and its definite chemical composition is sodium and chlorine. So all of those little cubes you see there are comprised of sodium and chlorine atoms that are chemically bonded together. So that is by definition what a mineral is. And if you haven't guessed it yet, that is salt. So that is table salt. But if you're talking to a geologist, they refer to it as halite. That's actually its name. So rocks, it didn't come up on this slide yet. So what is the difference between a rock and a mineral? Minerals are the ingredients that make up rocks. So when I take minerals and I combine them together, then I make a rock. So there is a difference between rocks and minerals. Minerals make up rocks. Now we classify minerals by a lot of different ways. We can use color. We can use density, which remember is mass per volume. We can use hardness, and we're going to talk in a little bit about what that means. Luster, I'm going to talk about that too, and then crystalline structure. All of these things are characteristics that we then use to identify minerals. So there's actually more than 4,000 different types of minerals on Earth, and a lot of them are made up of the two most abundant elements in Earth's crust, or they can contain those two abundant elements, and those elements are oxygen and silicon. So oxygen and silicon actually make up a very common rock that we're familiar with, and that is quartz, which is essentially silicon and oxygen chemically bonded together. So yeah, more than 4,000 minerals on Earth. So identifying minerals. So the first thing that we usually go to is color, because I can see it. It's what my eyes pick off right off the bat. Color of minerals are actually caused by impurities. So when those minerals are forming, you get other elements inside there, and it will cause that color difference. This one is a very recognizable mineral. Bright yellow in color. If you could have smell-o-vision here, you'd actually smell it. It smells like rotten eggs. This is the element or the mineral sulfur. Sometimes minerals are clear, so you're not going to get color to them. That second one that I just clicked on, that is actually a quartz crystal. You can see this last one here, the purple one. All of these colors are caused by impurities, but I can see, and I got another orange one that pop up here, that's a real just bright obvious thing that pops out to me is their color. The bad thing about using color as an identifier for minerals is sometimes it could be changed by weathering. So what that means is when these minerals are outside, they're exposed to oxygen, they can actually possibly change color. So if it's changing color, that's not helpful for you to be using it as an identifier. So pyrite, for example, also known as fool's gold, when it's outside, it will actually oxidize and kind of turn into this really, dark, grayish, silvery, brown color, and it's not going to look like you see the picture on the left-hand side there. So color is usually not the most reliable indicator to identify a mineral. So yeah, we look at it first. It's what we go to, but it's not what is probably the best thing to use if you are trying to identify a mineral. Crystalline structure. Every mineral has a definite crystalline structure that can be used to identify that mineral. So I showed you halite earlier. Halite has what we call a cubic crystalline structure, and that means every halite on this entire planet has a cubic crystalline structure. So if you're looking at a mineral and you look at it and you see it has a monoclinic crystalline structure, you don't have halite. Halite is always cubic. So there's the 7 basic. We're not going to go into those, but just know that you can use that crystalline structure as an identifier for those minerals because they will never, ever change. They are always true to that mineral. Your book talks a little bit about how diamond and graphite are both minerals that are made of the element carbon, but really the only difference is the crystalline structure, whereas graphite is made in sheets and diamond has crystalline structure. Graphite's made in sheets, and that's the reason why that we can write with it. When you write with your pencil, you slough off layers of graphite. Diamond was just formed deep under Earth's surface, extreme pressure, which caused it to set up that beautiful crystalline structure, and graphite did not get that case. So they're both made of the same thing, but essentially you have two different substances because of their crystalline structure. Hardness of a mineral is really what its name implies. So hardness is a mineral's resistance to being scratched. So if a mineral is harder to scratch, it's going to be harder. What we use in geology is called the Mohs hardness scale. It goes from 1 to 10. The softest minerals are going to be 1, and then the hardest minerals are going to be 10. Now, there's some common tools that a geologist will carry around with them, and they can kind of use that to do what we call a scratch test on these minerals. For example, your fingernail is about a hardness of 2.5. So if I can scratch my fingernail on the mineral, then I know the mineral is less than 2.5 on the hardness scale. When you look at these things, if a mineral is harder, it's always going to be able to scratch a mineral below it. So for example, diamond will have the ability to scratch corundum, but corundum with the hardness of 9 on the Mohs hardness scale is not going to be able to scratch diamond or 10. Steel tool is about a 6.5, so what geologists will often carry on is actually a nail with them, and you can use that nail to scratch things. So if you know the nail doesn't scratch it, it's going to be harder than 6.5. If the nail does scratch it, it's going to be less than 6.5. So now you can start to see all of these things start to be little clues that help us figure out what the identity of a mineral is if we're trying to figure out what they are. So that Mohs hardness scale we were just talking about, like I said, goes from 1 to 10. 1 being the softest, 10 being the hardest. It's been around for a really long time. Friedrich Mohs, in 1812, was an Austrian mineral expert, came up with it. The minerals that you see on the side there are very common minerals that if we were in class, you'd be able to touch them and see them, not the diamond, but definitely the talc. Talc is a really soft mineral. It's so soft you can scratch it with your fingernail. Remember, your fingernails are rounded 2.5. It's so soft that they actually used to grind it up and use it in beauty powders. So there it is again. So 1 to 10, 1 softest, 10 hardest. Your fingernails are around to 2.5. Pennies are around a 3.5. So that's another thing we'll sometimes use. And glass is around a 5.5. So that's why, if you have diamond, you can actually cut glass with it, right? If you have any of these things, topaz, quartz, corundum, they're going to be able to scratch that. Streak is the color of a mineral in powdered form. So what you see on the picture here, that is actually what we call a streak plate. It's a piece of unglazed ceramic tile. So it's just like what your bathtub might be made out of or your toilet. And instead of putting that shiny covering on the outside of it, they don't do that. If I take the mineral and I rub it across that streak plate, I can see a color. And as you see in the picture here, it's not the same as what the mineral is all the time. Very reliable indicator for a mineral. So whereas color will change because of weathering, streak does not do that. So streak is not affected by weathering, whereas color is. So it's a much more reliable indicator for the identity of a mineral. Density, we've learned about this before. So density is mass divided by volume, remember? Every mineral has their own characteristic density. Just like we know water has a characteristic density of 1 gram per milliliter, minerals will have the same thing. So for example, graphite has a density of 2.3 grams per cubic centimeter. If you have this gray mineral and you're thinking it's got to be graphite, you go to do the density test, it's 4.9 grams per cubic centimeter, you don't have graphite. It doesn't matter. Remember that's true for density. It doesn't matter the size of it. That characteristic will always stay true to whatever you have. Galena, here's another silver one. When I look at it, oh, maybe this was graphite. No, when I do the density test on it, look at it there, 7.4 to 7.6 grams per cubic centimeter. It's actually a much heavier mineral. When you pick up galena, you can feel the weight to it. It actually contains lead in it, and that's the reason why it is heavier. This is one of the things that we use to get lead out of the environment. And yeah, we use lead for a lot of things. Think of any time you've gone to get an x-ray before and maybe you've worn a lead vest or the nurse wears a lead vest, and that's usually where they're going to be getting it from. Luster is going to be how a surface reflects light. So here's a slide that just shows us a few different types of lusters that we have. Talc is greasy. If it's vitreous, it looks more glassy to it. Resinous is more plasticky. Sometimes they're dull, like the mineral hematite. All of those things are what we call the mineral's luster, so how they reflect light. Metallic, that's another very common one. If it looks like a metal to it, think of like a chrome on a bumper, that's going to be a metallic luster to it. Some minerals actually have a special property to them. So for example, we used halite earlier. Halite we put on our food because of the taste of it. So some minerals have a taste property to them. Some minerals will react chemically with things. So for example, if you put hydrochloric acid on certain minerals, they'll start bubbling and fizzing. Some of them will have optical properties. Calcite, for example, when you put calcite over writing, it actually doubles the image. There's another mineral called eulexite. When you put that over the image, it projects the image up on the surface. It's called the TV rock. It looks pretty cool. Fluorescence, some minerals have the ability to fluoresce. So when you put them under a black light, they actually glow really super cool colors. Some elements are actually also radioactive. Some are magnetic, like magnetite. So some minerals do have these special properties. Another characteristic we can look at with the minerals are what are called their cleavage plane. So some minerals, when they break into nice, smooth planes. When they do that, we say that the mineral displays cleavage. So a cleavage plane is a surface along which a mineral cleanly splits. If a mineral does not do that, then we say it does not display cleavage. The mineral mica is a beautiful example of a mineral that displays cleavage. You could sit here, and I don't know if you can tell in the picture, but you could literally just flake off layer after layer after layer. That mineral displays cleavage. Where if you take a mineral like quartz, for example, I go to hit quartz or I go to try to peel it apart, it's not peeling apart and it's just going to break into pieces. So if it breaks into thin planes or long, clean planes, we say the mineral displays cleavage. So all of these things that we just talking about for minerals that we use to identify minerals, those minerals are what make up rocks. So rocks are naturally formed solids and they are made of one or more minerals. So here's a rock. I can see inside the rock, I see the minerals quartz, I see feldspar, there's mica. So those things are the ingredients that make up rock. So we have three major types of rocks that we're going to talk about in the chapter. And those three major types, well, that are on Earth actually, those three major types of rocks exist because of how they were formed. And we're going to talk in much greater detail about them later on. So I'm just going to mention them now. So igneous rocks are rocks that form from the cooling and crystallizing of magma or lava. Sedimentary rocks form from sediments that become compacted or cemented together. And then metamorphic rocks form from other rocks from heat and pressure. So they're cooked or they're squeezed. So those are our three types of rocks that we find on Earth. So it doesn't matter what type of rock you find. If you're out, I think it's called spelunking. If you're out looking for rocks, and I'm not afraid to admit it, I love finding rocks outside. Those rocks can be put into one of these three categories. If it came from magma that cooled or hardened, it's igneous. If it came from sediments that have been compacted and cemented together, it's a sedimentary rock. If it came from extreme heat and pressure, then it's going to be metamorphic. So those are our three types that we're going to talk about in this chapter. So when you guys think igneous, think magma, think lava. When you think of sedimentary, think of these sediments getting compacted and cemented together, and then metamorphic is essentially cooking the rock, but you're not going to melt it, or squeezing it would be another way. And then we're going to learn about in the last section how these three types of rocks essentially change into each other. So at any given time, you can have them turning into each other, or they become new rocks. All rocks on Earth are part of the rock cycle. They're constantly cycling and changing and moving into other rocks.